We're returning to Chapter 6, the momentum equation, and we're going to just do one more section in this chapter, and it's, whoops, it's 6.5, and we're going to look at inertial and non-inertial reference frames. Basically, we're going to apply the linear momentum equation to moving objects. We're going to use a rocket as an example, and we're just going to show some key concepts for how you deal with momentum accumulation when you have a moving object. We are going to skip section 6.6 on rotating objects, primarily because we skipped the rotation stuff in previous chapters. So let's go ahead and go forward to section 6.5, and we see our familiar graphic here which shows the problems that we can solve with the momentum equation, and we have already talked about stationary control volumes, those for jets, vanes, nozzles, and pipe bends, and we are now moving over into this other branch over here dealing with moving control volumes. And we have two different types. We have things that are moving at a constant velocity and objects that are moving or at control volumes that are accelerating. So the first thing that we need to do is understand the concept of reference frames, and in particular an inertial reference frame is one in which the object is stationary or moving with a constant velocity, and that's with respect to the Earth. So with respect to Earth, where Earth is our kind of our base reference frame. So if we have an object that's accelerating with respect to Earth, which is we're going to consider an inertial reference frame, then that reference frame will be non-inertial. It's very important to realize that the momentum equation is valid only in an inertial reference frame. So we must find one of these, we must basically define our reference frame to be one that is either stationary or moving with a constant velocity. So the book does, let me skip ahead here, the book does has a great example here of showing when you would have a system with a constant velocity. So you should take a look at this particular example in the book. And what we have here is a nozzle. The example shows that we have a 50 meter per second jet coming out of a 5 centimeter squared jet here, or nozzle, and we can certainly describe the momentum coming out of here of the fluid, but that is hitting a vane, but the vane in this case is moving at a constant velocity. So you can see that what we're going to have is we're going to have the speed of the jet coming out, the momentum of the jet coming out in this direction, but the block is retreating from that momentum. So we're going to basically, if you look at the solution, you can see that the momentum is going to basically be the difference is going to depend on the difference between the velocity of the jet and the velocity of this vane or block here. So have a look at that. This slide shows the difference between these inertial and non-inertial reference frames. And so when you're in a reference frame that's fixed with the Earth, with respect to the Earth, that's going to be inertial. So if you see, and this is a case where this nozzle is fixed with respect to Earth, and this block is moving at a constant velocity, not accelerating. So the rocket is a totally different situation, because usually we have the velocity of a jet being ejected out the bottom of a rocket, which is propelling the rocket upward, and it is accelerating from 0 to basically whatever speed it's going to reach before it exhausts its fuel. And so it starts from velocity of 0, but accelerates as that velocity changes. So let's take a look at this accelerating reference frame. So if we were to do a force diagram on a rocket, what we find is that there will be a drag force and the weight forces in the negative z direction. And the pressure force, the pressure of the ejected exhaust and the area of the exhaust here is going to be the pressure force acting in a direction, a positive z direction, to propel the rocket forward. So basically what we have is a jet of fluid coming out the back of or the bottom of the rocket, but that's creating a pressure inside the rocket, which is propelling it upward. That's going to be pressure above gauge, above atmospheric pressure. And so the sum of the forces in the z direction then are really just this pressure force, which is propelling it upward, the minus the weight and minus the drag. Now on the right here, if we look at the momentum, we can see that we have only outflow. There's no, through this control volume, there's no inflow of momentum anywhere. We just have an outflow. This is going to be equal to the velocity of the momentum outflow is going to be, at least from the reference, from the point of view of the inertial reference frame, it's going to be the mass flow rate times the difference between the exhaust velocity minus the actual velocity of the rocket. But what is very key here is that this accumulation term, this is the accumulation term in the momentum equation, the total derivative with respect to time of the mass of the rocket times the mass of times the velocity of the rocket. That is actually not zero in this case because the rocket is accelerating. There are two reasons why this is so. If we look at this total derivative here, note that dmr, sorry, whoops, I guess I'm not going to be able to cancel that out. Let me just see if I can erase that. Nope, I can't erase either. Let me just start this equation again. So d of mr vr with respect to dt, that is going to have two different terms. It's going to be vr times dmr dt. Normally we would consider the mass with respect to time to be equal to zero, but in this case it's not. I'll tell you why in a minute. And that's going to be times mr dv dt. This term, the second term here, is our normal acceleration. The fact that the rocket is changing velocity as it accelerates upward. This term here represents this mass change is really the mass of the rocket, and that is changing in time as the rocket loses fuel. So let's go on to the next slide and look at the equations. So if we start to try to write down our momentum equation, which we have up here, let me reduce this. We look at our sum of our forces. This is the left-hand side. The Lagrangian point of view is going to equal to the momentum accumulation. This is the momentum accumulation term, plus the outflow minus inflow. And we know that this term here, the inflow term, is zero. So if we look only at at this term, if we expand this term out, we can see that this is going to actually, if we work out the math here, this is the dmr vr dt, basically the accumulation term of the rocket. And what happens here is if you look in the book here, you'll see that the book uses the continuity equation to show that this is true, that the rate of change of the rocket's mass plus the outflow, basically the mass flow rate, has to equal zero. So as the outflow, basically as the rocket loses mass, that has to equal the outflow or minus the outflow. So this equation actually turns out that is going to cancel this term right here. That you're going to have VR dmr dt is going to be equal to minus m. I'm sorry, plus m dot VR. Um, because of this continuity equation right here. And so we can see that that's going to cancel out from this term. That's going to cancel out the v. There's still one term left of this total derivative, and it's basically the mass times the derivative of the acceleration. But the other term, the velocity times the change in mass with respect to time, is going to cancel out with this. That's why that kind of magically, this kind of VR kind of magically disappeared from this equation. So the points are about this. If I summarize what I just said, is that the accumulation term is not equal to 0 in this case. So we need to deal with it. And we see that it has two parts. And in this case, by using the continuity equation, we see that we can cancel out this term and half of this term here. This gives us a resulting equation for the momentum of the rocket. Now, the book also goes about saying that if we kind of collect some terms on the other side, basically the momentum of the jet and the pressure of the created by that jet is going to be equal to what's called the thrust, and that can be expanded out into this just by writing out the mass flow rate. In terms, it is rho AV, and so we have an expression for the thrust of the rocket. The book also describes a term called the burnout velocity, which is given by this equation here. This is just, again, a rearrangement. And a lot of times they will just ignore the drag and the weight. I'm not actually sure why they do that. That seems very strange to me. That seems like a bad assumption to do that. But they reduce the thrust equation to just being the thrust equals basically the acceleration of the rocket. And from that, they can plug in for this value of the thrust into here, and they can solve the equation for what's called the burnout velocity, and they get this. So the keys, that's all I'm going to say about this. But the key to this section is because this is an accelerating body, this term in the momentum equation has to appear. This is its value, and we have to deal with the total derivative, both parts, both the mass changing and the velocity changing. But because of the way this problem is expressed, that the mass, this term, we can use the continuity equation to eliminate that dmr dt term, and we're left with a final equation that has basically the momentum of the jet, the pressure from the jet, the weight of the rocket, the drag force being equal to how the rocket is accelerating. So that's it for this section, and that's it for chapter 6. Next lecture will be on chapter 7.